What happens when an ambitious builder tries to join two skyscrapers high up in the Manhattan skyline?
So you can't call a friend and say, hey, what did you do the last time you built a bridge 300 feet in the air in New York City?
How does this huge wing-like roof not take flight in gale force winds?
The whole canopy has an ability to move 15 to 20 centimeters.
And how can a building be constructed without a corner in sight?
It kind of goes against everything we think engineering should be.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now their secrets are revealed, discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? New York. With the total area of buildable land worth over $1.7 trillion, its eye-watering prices have created one of the world's most memorable and expensive skylines. With space at a premium, it's forcing developers to come up with groundbreaking solutions to make the most out of even the least inviting scraps of land. Developing one awkwardly shaped plot in Midtown Manhattan tested engineers to their limits, leading to panic on the streets.
Hear the fire department, they pull up and the guys come screaming and they're running in and we got a call, one of the buildings is falling down.
And creating the city's first sky bridge in 80 years, giving rise to one of New York's most incredible new skyscrapers. This is the American Copper Building.
Building two skyscrapers, wanting to join them in the middle, and then deciding that actually you want them bent, that is next level.
In 2013, developer JDS had its eye on a plot next to the river that should have been prime real estate. But the site came with a major problem: New York City's zoning laws. The rules that decide what can be built and where.
The zoning of this site was prescribed before we bought the site. That approval prescribed the exact footprints of the tower and the exact heights of the tower. They assumed by prescribing the footprint and the height that they were prescribing the exact building shape. But when we bought the site, we didn't want to create two buildings. We wanted to create one building.
There was an existing building in the corner of the plot and a piece of land that had been zoned as a park. So how could they create their dream of a single building?
We didn't want anyone to be going to the gym in their neighbor's building. We didn't want someone going to a lounge or going to visit someone else in a neighbor's property. We wanted to use the scale of the property and the block to create one community.
JDS brought in Greg Pasquarelli from Shop Architects to find a solution.
When our client bought it, he said, I could go through a rezoning, which takes many years and has a lot of risks and it's very difficult. Or he said, can you come up with something with these handcuffs on? And that was our challenge.
They could have built two towers, but they came up with a much better idea.
There end up being a lot of great ideas, a lot of terrible ideas. And what usually ends up happening is one of the terrible ideas turns out to be a really wonderful one. And it's terrible at first because somebody says, let's build a giant bridge between two buildings, hundreds of feet off the ground. And for those of us that have to pay for it and figure it out, we go, no, let's not do that. But of course, as you start to wrap your head around kind of all the different aspects that could make it possible, you start to realize that it's actually very approachable. And the way we approached building the Sky Bridge was the same way we approached building everything else, which is kind of one step at a time.
It would be the city's first sky bridge in over 80 years. joining two giant skyscrapers 90 meters in the air on the banks of the East River on a site prone to flooding was always going to be an engineering headache. But it was also an opportunity.
The idea was we could make a sort of amenities package or a shared space that would be sort of typical for each building. Or if we built a bridge, we could build one phenomenal one that brought everybody together. And so getting that designed and built and making it work was the greatest challenge, but I also think is the greatest success of the project.
The easiest way to connect the two towers would be with a straight line. But that would mean going over the existing building which they didn't own. The architects came up with a gravity-defying solution. They decided to bend the buildings.
How did they bend the towers? That's the real question.
They bend towards each other, right? One on the long axis and one on the short axis. It moves the edge of the West Tower out to the corner of the property line so that we can actually connect the two buildings with a straight line. Otherwise, our bridge would have had to be kind of L or V-shaped, which is obviously much harder still to do.
By bending the two towers, they'd not only overcome the zoning issues, but also the engineering ones.
Making small adjustments is a great way to make a big change. A couple of inches can quickly become meters, and it's something that clever designers can use to their advantage.
And that's exactly what they did here. By slightly moving each floor closer to the other building as they go up to the sky bridge, and then moving away again, they were able to bend the buildings.
We were able to solve both of those problems with these really elegant architectural moves.
In 2012, work began preparing the site for construction. It was clear from the start this was going to be a tough build. The site was right next to the East River, a location that had previously flooded.
It's in an area that's subject to hurricanes. So in 2012, there was a very large hurricane, Hurricane Sandy, which affected New York. And during that hurricane, this actual site was flooded before the building was constructed. So that's really highlighted two of the main risks to the construction, the wind and the water.
The man who had to face this challenge was Michael Jones.
The foundation of the building was kind of a monster process on our end to build it. We're very close to the East River and the water level is very high. So to dig a hole as deep as we had to dig it and do all our foundation elements was a serious challenge.
Michael and the team had to dig down 15 meters. But with the water table only 1.5 meters below the surface, they needed to stop the site from flooding. The engineering solution was to create a huge concrete structure to keep the water out.
What you do is you create a perimeter wall around your site from the ground level. You can push steel sheets and you push those down into the ground and they interlock. And so you more or less build a bathtub with no bottom. And then the water level is inside the bathtub is the same as it is outside. So then what you can do is you drill wells down there and you de-water inside of your bathtub. You can locally bring that water level down by putting a pump. You have to kind of artificially drop the water level. And to do that with a few cups of water is really easy. To do it with a few million gallons is difficult.
It took 1.5 years to do it. But with the bathtub built and the foundations in, they could turn their attention to the next big engineering challenge. Building the bending towers.
Generally, a leaning building is very much a bad sign. And the designers would very much have had to have factored in the kind of sideways forces that are caused by something leaning. But there's two things to consider, and that's that they've designed a building that's able to lean, but also that that building is going to be leaning throughout its construction, which means you have to really think about the stability of the final building, but also all the intermediate stages during construction. So it's an engineering feat.
The person making sure this bent skyscraper didn't come crashing down was structural engineer Susan Hamos.
Because of the leaning of the building, every floor we had to tie back to the shear walls, which shear walls means they take shear, they take horizontal load, they take shear from the wind loads, shear from the seismic loads, and shear from gravity loads. You imagine if you put something like this wants to fall down. So we had to put some rebars to pull it back to the vertical long concrete walls that were designed to take all these horizontal loads from the gravity.
Although the building bends, the lift shaft and the shear walls stay vertical and act like a spine, taking the force of the floors as they create the bending skyscrapers.
The main structure, which is the core, the elevator core, and the shear walls, which are massive structures, those stay straight, but all of the columns were on an angle. So we got really good at building columns on an angle.
As the extraordinary skyscrapers took shape on the Manhattan skyline, they didn't go unnoticed.
This tower, the East Tower, goes about 8.5 inches per floor. So by the time we are really offset maximum distance, we're over 20 feet, 22 feet, I think it is, out of plumb before we start working our way back. And that's the sort of visual thing that people really weren't accustomed to seeing.
The bent shape of the skyscrapers caused panic as the buildings were going up, which is something that the main builder had to deal with.
One day, we're down there, we're all working, and you hear the fire department, they pull up, and the guys come screaming, and they're running in, and it's a little chaos for a second. We're trying to figure out what's going on. And finally, I grab the guy, I go, what's going on? What's happening? I'm in charge here, what's going on? He said, we got a call. One of the buildings is falling down. And I kind of stopped and I had to think about it for a second. I go, no, it's supposed to be like that. Showed him pictures and renderings of the building and showed him the plans and everything, but it's such a unique architectural feature that people didn't know how to respond to it.
Once the builders had convinced New Yorkers the towers weren't collapsing, they still faced one of their biggest challenges: the Sky Bridge. Central to the design, the Sky Bridge, 90 meters in the air, would join the two towers together, making one community.
The bridge is several layers. There's private terraces on top, there's a public lounge in between, there's a pool and hot tubs, so you can kind of swim from one building to another. And then below all that, the bottom level of a bridge, we use to transfer mechanical water, and we use emergency generator power. We transfer from one building to another. And that's really my favorite part, is that it allows us some kind of leeway in terms of where we put equipment, so each building doesn't act isolated to each other.
The bridge came with some serious engineering challenges. How would they stop the hurricanes that regularly hit New York, tearing it apart?
The biggest design constraint on tall buildings in New York is wind. So buildings move back and forth towards each other and away from each other. The total movement between the two buildings is about 12 inches. 12 inches is in a windstorm. So that movement is our number one challenge. From a structural perspective, that sky bridge is like putting a toothpick between two rocks.
Skyscrapers are built to cope with high winds, and at the top can move around a meter in any direction. Fine when they're not fixed to another building, but here, two independently moving towers would be linked by the bridge, and when they moved, they could rip the bridge apart.
Is it possible to put a bridge there? We said, of course it's possible. So how will we do it? And we said, no problem. We'll connect it to one building and we let it slide on the other. So when the wind is hitting the two buildings, one would move out, the other one would move in, and we don't want the bridge to buckle, to pop out of its place. So we have to slide it on one side.
Their solution was to join only one side of the bridge to the towers and balance the other side on huge Teflon plates, letting the bridge slide in and out of the East Tower.
It slides on these giant Teflon plates that account for 28 inches of movement in total, 14 in any given direction.
Now they knew it was possible. All they had to do was build it.
Unfortunately, when you're doing something unique like this, you can't call a friend and say, hey, what did you do the last time you built a bridge 300 feet in the air in New York City?
Building a 90-meter high and 75-meter wide scaffold tower between the buildings to allow construction of the bridge would be difficult. So they decided to build a temporary bridge from which they'd construct the real one.
We were trying to figure out the best way to do it, and it started with someone was supposed to bring a football in. We were going to tie a string to it and kind of throw it from one building to another, but I think we forgot the football that day, so we took a stick and wrapped it up with a bunch of literally small string, made sure everything was clear below, everything was safe, we were good, threw it from one building to another, and so we had one string. Then we pulled back a string that was a little thicker. Then we pulled back a rope, then we pulled back a thicker rope, and then we could finally pull back the steel cable and literally just started weaving the cable back and forth until we got it. From there, we could work off there and start building the bottom of the bridge, build another platform, build the next level of the bridge, and so on.
With the temporary bridge in place, Michael then had to figure out how to lift the huge sections of steelwork 90 meters into the air.
We were limited with what equipment we could actually lift it with, because as you can imagine, lifting something very heavy, probably 40 to 60 tons at that height, over 300 feet in the air, requires a serious piece of equipment, and you can't always fit serious piece of equipment in New York City.
To lift the giant steel trusses, the skeleton of the building, into place, the builders attached a tower crane to the skyscraper to stabilize it against the wind.
Now that we know the maximum piece of equipment we can get in here, how do we break the bridge into pieces that that piece of equipment can lift, and so that we can then construct it?
210 tons of steel had to be hoisted the 90 meters up, one piece at a time, to where the construction crews could connect them. With the sky bridge in place, work began on fitting the extraordinary copper facade.
They're called the copper buildings because they're covered in over 4 million pounds of copper.
Like everything else on this project, creating that copper finish was not going to be easy.
First time this idea was presented, we thought we'd have to put copper plate on the outside of the building. And we did the math on how much copper we'd have to buy, and then looked at the raw material price of copper and realized that we'd have to pay more for the copper just to get it here than we paid for the property itself, which means that we couldn't afford it. And so what we ended up doing was coming up with a pretty unique laminating structure where the copper face, which is very, very thin copper foil, actually thinner than what's even on a penny, and it is laminated to a fireproof core, and then on the back side of that core is stainless steel.
The raw copper is then left untreated and open to the elements.
Copper's gone from shiny, penny-colored, and it will patina and continue to turn green.
The rest will be done by the weather over the next 50 years.
It's gonna be beautiful. I can't wait for that. I love the copper, but there's something very American about that color green, especially in New York. It reeks of kind of old, beautiful New York buildings, all the flashing, but ultimately it reminds me of the Statue of Liberty, so can't wait for it.
The designers and developers have truly built the incredible from the impossibly difficult.
The American Copper Building takes its place in the New York skyline as a testament to how ingenious engineering and clever design can create amazing living spaces in one of the world's most crowded cities.
Two spectacular buildings forming a single iconic project. It's a real engineering achievement.
Taking this kind of restrictive set of rules and celebrating it into something that looks beautiful and inspiring and makes people wonder about it. Whenever you can do that as an architect, I think that's something you should strive for.
"5,000 miles from New York, in the ancient Greek city of Athens, engineers and architects have been battling Mother Nature to create an enormous 10,000 square meter floating roof.
To my knowledge, it's the first application in the world.
Over €500 million created a cultural center for all Athenians. Complete with a new hill with a public park on top.
This isn't just about creating a building. You're creating geography.
And all of which has to be tough enough to withstand any potentially devastating earthquakes.
Building in an earthquake zone is a dangerous game.
So how did they build it? In 2006, the Stavros Niarchos Foundation, a wealthy philanthropic organization, wanted to give a new home to Greece's National Opera and National Library. They wanted somewhere that would inspire the people of Athens. Eli Andropoulou helped manage the €566 million grant given to build the Stavros Niarchos Foundation Cultural Center.
Pushing the boundaries of architecture and engineering wasn't a goal in itself, but it was a very important means to achieve the vision of the SNFCC. So we didn't want to just provide new premises to these two national organizations. We wanted to give them a new home, which would become a landmark. There were a lot of risks taken. The people involved in the project were very passionate about pushing these boundaries, and they certainly had the expertise to do so.
The foundation turned to the company that had transformed the London skyline with the Shard, the Renzo Piano Building Workshop. Giorgio Bianchi oversaw the project.
We had in mind this idea to raise the land in some way and hide the opera and the library under something like a hill. The hill was the park. I create my hill, and on top, I put the solar canopy. And then I plant my park. And here you have the opera house and the library. Easy.
Building it would prove to be anything but. The futuristic buildings would hide behind a massive 32-meter-high artificial hill. At one end, the new earthquake-proof complex would be home to the Greek National Library and the 28,000-square-meter National Opera building. It would be topped off with a huge square floating canopy, 100 meters long, that would protect the complex from the fierce Greek sun and generate electricity to run it from 5,700 solar panels. Many of the building techniques needed had never been used in Greece before.
There were certainly many challenges during construction because we were pushing these boundaries in engineering. The canopy was certainly a very challenging element. The hill in the park, the seismic isolation of such a large building, all of these challenges were overcome and led to great innovation.
One of the most important challenges was going to be protecting it from the Earth itself.
Greece lies on several fault lines and has a long history of earthquakes. Traditionally, though, Athens has remained unscathed. Unfortunately, that changed in 1999 when an earthquake hit and killed 143 people.
In 2018, Greece was hit by nearly 300 earthquakes. Quakes greater than 6.3 on the Richter scale can destroy a building.
If you're creating any new building in Athens, you've got to take earthquake risk seriously.
Structural engineer Gregory Pinellis was part of the team that took on the challenge.
Greece has actually 50% of the seismicity in Europe. So it's obviously a very seismically prone area. Such a complex structure was obviously a challenge, not only because of its complexity, but also because of its criticality, considering that it is an opera that has thousands of people inside when in operation. So seismic safety was a very big issue for the design of this building.
With millions of people expected to visit each year, they couldn't take any chances.
The purpose of any structure is to carry load or forces from where they are and down into the ground, and that's true of anything, from buildings, bridges, chairs, and my skeleton. But when you have an earthquake, then what's happening is that the ground is shaking violently from side to side, and it's that sideways force that has to be carried down into the foundations. So if a structure is in an earthquake zone, then it has to have a way to resist that sideways motion, or it will fall down.
Most buildings are made to resist forces from the top down. But with an earthquake, you get sideways or lateral movement that can easily destroy most structures.
Both the opera and the library are actually seismically isolated. Seismic isolation is like you put the building on rollers. So when the earth moves, because the earth moves, not the building, it moves underneath and the building stays the same. A very easy analogy for the non-engineers is when you have a wooden table and on top of it a toy truck, and you move the table and the truck stays without movement. The table moves, or when you take the tablecloth under the plates and the plates stay, if you can do that.
All well and good in principle, but how do you pull it off with two huge buildings?
Here we are in the basement of the opera. We are at -2 meters from the sea level, from the ground floor. Every column of the opera and the library has a seismic isolator underneath it. And underneath the seismic isolator, there is a concrete pedestal, and then we are standing on the foundation of the building. So the whole building is seismically isolated from the ground, so that when the ground moves due to earthquake, the building remains stable. So when the earthquake happens, the pedestal and the ground moves with a tolerance of 35 centimeters back and forth each way. One of them is actually the largest one ever installed in Europe. The critical thing is how we design all the mechanical and electrical and architectural features of the building that connect the ground to the upper stories so that they can follow this 35 centimeter movement.
Allowing a building of this size to have 70 centimeters of movement requires an awful lot of forward planning. Every wire, every pipe that's going in and out of this building requires an extra flexible section in order that they don't break when the building's moving.
Every wall joint and every staircase has to have a movement gap, which they then fill with silicon filler. When the building shakes, the silicon breaks. That's a lot of filling and repair work, but it's much better than the alternative.
Their next challenge was to create the enormous 32-meter high hill that gives the building its signature shape.
This isn't just about creating a building. When you're making a whole new hill, you're creating geography. They've actually altered the skyline of Athens.
This 300,000 cubic meter hill is made up of enough dirt to fill 120 Olympic-sized swimming pools. 3,500 gravel pillars had to be constructed underneath to hold the soil in place and prevent landslides. Then, the top was planted with over 1,000 trees. The effect of creating the park was to lower the local temperature from the shade the trees generate. The hill, though, had another purpose too.
It was just to give back to this part of the city the idea that they have the sea very close, and they can use this area to get to a point that where the sea is visible again.
At the summit, looking over the Mediterranean Sea, sits the engineer's greatest achievement, the canopy. A huge technological marvel that needed engineering solutions used nowhere else in the world.
It is a structure that's 100 meters by 100 meters in plan. The magnitude of this and the need to create a very large structural span of more than 75 meters clear span led to a lot of innovations.
There are 750 panels creating a 100 meter by 100 meter canopy that simply floats on the Athens skyline. It's a beautiful piece of engineering.
As well as being beautiful, the huge 4,700-ton canopy had to survive the Mediterranean storms that hit Greece every year. With wind speeds reaching over 60 miles an hour, the canopy had the potential to act like a giant wing and be ripped off the building. The engineers had to come up with a solution. They decided to make the roof so it behaves like a spoiler on a car, creating downforce when it's caught by the wind. So instead of lifting, it pushes down onto the supporting pillars. To test it out, they built a model to see how the wind would affect the roof. Its aerodynamic shape could survive the powerful storms. They then had to find a material that was strong enough to span the huge distance and cope with the force of the wind. They chose ferrocement.
Ferrocement has been used extensively in boat building, so tankers were built from ferrocement in the 70s. And also it was used as cladding material for very elaborate buildings.
Ferrocement is made of a fine wire mesh with a thin layer of concrete. It was first invented in the 1840s in France and is thought to be the first ever reinforced concrete.
Ferrocement confounds our expectations about what concrete can be used for. This is concrete that is thin and delicate and light.
Ferrocement can be made much thinner and outperform traditional reinforced concrete. But that requires an exact combination of cement and reinforcement.
We needed to go through very extensive testing for the ferrocement.
When tested, the 5-centimeter thick panels were able to support nearly 1,000 tons of force per square foot, the weight of 6 blue whales.
This thin mesh of 1 millimeter diameter is not produced normally as a structural material, it's produced as a fence.
The ferrocement was thin enough to keep down the weight of the structure and strong enough to span 100 meters in each direction. The next problem was that the downforce of the canopy in high winds would be enough to push the supporting columns through the roof underneath. The engineers came up with a radical solution: to build the canopy its own suspension system.
Above us and below us is ferrocement. Now we can see it, the whole structure with the ribs, and we are seeing the suspension system of the canopy from the column.
Instead of sitting on the columns, the canopy sits on the suspension system, which absorbs downforce even in heavy storms.
The columns enter the canopy, and then it is suspended with a system of springs and dampers from the column. So it's hanging from the columns. Additionally, we have vertical brakes that don't allow the canopy to move for small winds. It only moves for large winds. The whole canopy has an ability to move 15 to 20 centimeters. This movement will only happen in a hurricane, once or twice per year. This is the actual frequency that we have vibrations of the canopy. To have the actual vertical load, 100% of it being suspended from springs, to my knowledge, it's the first application in the world.
The canopy isn't only for decoration. Its 5,700 solar panels generate over 2 gigawatts of electricity a year, enough to power 1.4 million houses for an hour, and most of what the entire complex needs.
This building is designed to be sleek and stylish, full of tech, really heavily engineered. It's a fantastic piece of engineering.
The SNFCC took 4 years to build. opening its doors to the public in 2016. The building is not only a testament to how modern engineering can realize the impossible, but built at a time of crisis in Greece, it gave hope to Athens and a modern focus to the city's history and heritage.
The SNFCC is for everybody, and it's a real gift to Athens.
This building has completely transformed the whole area of Athens. It has become a point of attraction for all Athenians. Not only Athenians, for all Greeks.
I think this is one of the most important things, if not the most important thing that has happened in Greece the last few years. And I'm very proud that I was part of it and very fortunate.
Named one of the world's most beautiful cities, modern Singapore certainly has some incredible buildings, but it also has some of the cleverest. Like the Hive, built for the Nanyang Technical University.
University buildings haven't really changed since the 16th century. Boxy buildings, teacher in the front, children sitting quietly.
It not only looks eye-popping, but has a revolutionary design. Classrooms with no corners, and a building that gets wider as it gets taller to create an eco-cooling system capable of combating the hot and humid Singapore climate, creating a building for the 21st century and beyond. Kam Chan Hin wanted a building custom-made to teach the next generation of students.
This building is very much designed for the millennials. The new generation of learners, they like to explore, they like to participate, and they go for quick images. The mobile phone is a good example. We felt that a building of this kind actually encourages students to speak up, to challenge assumptions, to talk to one another, and to learn from one another.
Heatherwick studio architect Matt Cash took up the challenge.
No corners. No corners, okay. Why no corners? And the idea being is that in a way, corners are defendable. Kind of, you can get your back to a corner and you're kind of like this. And it sets up a kind of a dynamic in the classroom between, again, the kind of the lecturer or the master and the pupils. And they didn't want to do that. They wanted it in the round. And it's if you meet at a round table, there's no hierarchy there. But a round table is completely democratic.
The innovations didn't stop there, because the university also wanted the Hive to be one of the most ecologically friendly buildings in the city.
We have an overall target to reduce energy consumption by 30%.
The only way to do that was to get rid of traditional air conditioning.
When we're thinking about the geometry of the building, we're thinking about how do you cool that environment in the best way possible, not using too much energy.
With a single room, we can air condition it. When we get to the scale of big buildings, though, it starts to get expensive and it's a massive drain on energy and resources. It's not eco, and we don't like it.
So the Hive came with two monumental challenges: to engineer a building without a corner in sight, and to keep it cool in one of the most humid cities in the world without air conditioning. Matt and the team got to work reinventing how a university works.
So we started with one classroom, which is in effect a kind of an oval shape. And then we took that one classroom and we arrayed it, we clustered it around a central atrium. And in a way, that clustering created the coming together. So each of the classrooms arrayed around a central space, and then they stagger up and climb. It's about, in a way, increasing student interactivity. That was really the beginning of the idea and the beginning of the form.
The Hive is made up of 12 8-story high towers that slowly creep outwards from the base of the building. Incorporating these circular classrooms had drastically changed the shape of the structure.
You've got a building that's getting wider and wider before it goes in again. It's much like a barrel that wants to fall outward.
building towers that get wider was far from easy.
Whenever you have anything leaning or at an angle, then it wants to move sideways, and there's that sideways force that also has to be resisted and carried on down to the ground. The consequences of not considering the stability correctly at all stages can be quite severe.
The engineers tilted the columns to work with the unusual shape of the building, letting them carry the weight of the floors above straight down to the ground below in one continuous motion.
The building kind of progressively steps out, so each floor is slightly cantilevered out from the next one. Now, when you're doing that with two kind of curving columns like that, the building wants to fall over. As the levels step up, at every level we have a ring beam, which is almost like in a barrel, where you have horizontal things that ties the barrel together. It stops the columns falling out, and that ties the whole structure together.
You don't often see leaning columns like that. It kind of goes against everything we think engineering should be. Straight up and down, solid, robust.
They may have overcome getting rid of the corners. Now they had to work out how to keep it cool.
Part of our challenge really was about the environment in Singapore. It's a very hot, humid environment. How do you cool that environment? And one way of doing that is to create an atrium in the middle. And atriums work by hot air, which hot air rises, rising up the middle, and then that drags air with it and creates almost like a chimney. And that chimney draws all the hot air up and away from the building. So the geometry was generated by trying to kind of cool the middle.
This is a form of passive cooling, which uses the form of the building to block, sink, and dissipate heat in a natural way. And it's a great way of really reducing the energy consumption, which is really important in somewhere hot and humid like Singapore.
The shape of the building draws hot air up and out of the roof. The constant flow of air cools it, and the hive's plants provide added shade, protecting the building from the sun.
The plants inside the building help to lower the temperature in the hall.
This building is totally energy efficient. It's been given the platinum mark for excellence in energy sustainability.
Matt had met the challenges set by the university, but he didn't stop there. He wanted a building that stood out.
We didn't have enough money to have a lot of different finishes. And so in effect, the floor, the walls, the cladding of the outside of the building is all concrete. People are expecting concrete to be grey, and that's the cheapest way of doing it. And if you had just a big grey building, it wouldn't have the kind of texture and relief that you would want. And so we experimented with lots of different ways of playing with concrete, treating it in a way like wet clay. On the cladding of the building, we use something called a retarder, which is, in effect, something that prevents the concrete drying at the same speed. And if the concrete's drying at different speeds, then some of it's hard and some of it's still wet, and then you wash that off. So some of the concrete exposes the stone, the aggregate inside the concrete, and some, the top surface, just a concrete finish. Having that variety means your eye kind of enjoys exploring it. And I think rather than understanding the building immediately, it kind of demands you look at it closer.
Although it's a radical design, the building's already won the hearts of the community.
It's called the dim sum building by some locals. That is because the shape also resembles the tiffin trays that are used to serve the dim sum.
It's obviously a really beautiful structure. It'd be a great and interesting place to work.
From what we know, the students actually love the place. Of course, it's very iconic. It's become a bit of a tourist spot. We're very proud of it.
The Hive created an environment that challenged the idea of how a university should work, and succeeded beyond all expectations, showing how engineering isn't only about keeping a building standing, it's about changing what's possible.